So loud. All right, so folks, let's give this a try. Seems like we've had to update how we screen share on my end, but that is absolutely fine. All right, so today we're going to be talking about section 7.3. So we are sort of marching our way through chapter 7, which is a lot of different identities. And as we're going through these, one thing that I noticed is that some of us are doing a wonderful job annotating which identities we're using where. I would very much encourage you to do that so that as you are working through things, you can continue to practice the old material that we've learned, as well as learning that vocabulary. And so in this particular section, we have a few new identities. One of the things that I feel like I try and do for you all is make sure we know what's going to come up again versus what isn't really going to show up again. Right. So like there are some things which we'll see like now, and then we won't see again until maybe a few courses later, or maybe we'll see something that we're going to see a lot in the next few courses. And so as students, I think it is important that we are able to sort of pick and choose what we store in our brains. Okay. And so let's start over here with this. Trouble picking my colors today. Today, we're going to talk about something called the double angle identities. All right. We're also going to talk about something called half angle identities. All right. So those will be the two main takeaways from today, double angles and half angles. But one thing I want us to note here with the reduction formulas, all right, these in the pink are optional. Yep. And for those of us who are continuing on several courses beyond this in our math careers, this comes up again in Calc 2. Okay, so this is the one in the pink is not something that you will see again in Calc 1, but it is something you'll see again in Calc 2. Okay. Now, again, I know we have so many different identities that we've learned so far, and I want to just be really clear that we're continuing to add to this list. And so what we know so far, we have a bunch of different identities that we've learned. Okay, some of them we started way back in the first unit, like the reciprocal, the quotient, odd even, cofunctions, Pythagorean. All right, so those first few ones came from the very beginning, whereas this sum and difference identities, those are the ones that you watched a video for on Monday. Okay. You also in that video saw how to evaluate sum and differences of main trig functions. And sometimes that can feel a little bit better because you're actually like getting a numerical answer rather than just trying to make two sides of an equation match. Okay. And the last thing that we're really building here in terms of like, how am I going to use this again is the algebra skills. And I really can't emphasize that part enough, that what we're really doing is building a foundation where when we walk into calculus in the spring, we're going to feel really good about the algebra. And then all we're doing is adding on the calculus part. Okay. All right. So what's new for today? We're going to take a look at finding exact values of double and half angles. We're going to verify trig identities. And I want to be really particular about what we write when we verify trig identities. I feel like some of us are taking note of what we write in the lectures and modeling that in our quizzes. And some of us are feeling like maybe we just don't want to write the same amount and now we're losing points. And however you feel about that is however you feel. I want to be very upfront and tell you, I do expect you to write both sides of a trig identity all the way down. Okay, so I want to make that really clear. So if you choose to do that, that's great. And if you choose not to do that, that's on you. Okay. The last thing I want to show again, and this is optional, I want us to take a look at the reduction formula just so we kind of see what it might show up like in a future class, right? Because I think a lot of times we're like, oh, we're going to use it again, but we don't know what it's going to look like or how grown up we're going to feel about our math skills when we get there. And so I think it's important to kind of see a little bit of that before we get there. All right. So we're going to start off with our double angles, all right, our double angle formulas. And the way we're going to do this, we're going to take a look at these formulas and we are going to talk about sort of where they come from, but ultimately what we want to focus on is what are these formulas, okay? The where these formulas come from part is more useful if you are working through a problem to kind of figure out like, okay, nobody just like randomly made these up, they actually came from somewhere. And so we have formulas for sine and cosine and tangent. And just by looking at these formulas, how would I know that these formulas are talking about double angles? Right? How would I know just from the equation that I was talking about double angles? Perfect.
There's like twos, yeah.
Yeah, we have this 2, right? Or in particular, we have 2 thetas. So it's like we have 1 theta and we're doubling it, right? We have a 2 theta here. We have a 2 theta here. Right, so all of those tell us, all right, these are our double angle formulas. Now, one thing to notice is the sine and the tangent, they only have 1 formula, but the cosine double angle has 3 different versions, okay? So we can write it cosine squared minus sine squared. We can write it 1 minus 2 sine squared. We could write it 2 cosine squared minus 1, all right? A note I would like us to make for ourselves is for the cosine one, when verifying identities, we will have to choose which version works for which case. All right. So yes, there are 3 of them. And the reason why there's 3 of them is because some, like one of them might be more helpful in one verification, whereas another one might be more helpful in a different verification, okay? All right, so we have these 3 identities. Let's talk very briefly about where they come from. All right, now this would be really beneficial if you folks have your sum and difference identities listed. All right, so I am going to ask you to sort of look back at your notes from the sum and difference identities and help me come up with some of these. All right, so let's start with our sine. All right, sine of alpha plus beta. Can someone give me the formula from Monday's lecture, video or notes, about what that formula is?
Sine A times cosine, well, sine alpha times cosine beta plus cosine alpha times sine beta.
Beautiful. All right, so we have this formula, right? And the way we used it is everywhere we saw the alpha, right? We did sine alpha, cosine alpha, but then where we had the beta, we had cosine beta and sine beta. And so now let's imagine we had sine of theta plus theta, okay? How would I rewrite this formula using theta plus theta instead of alpha plus beta?
The same way, but with theta.
Okay, so what would that be?
Sine theta, cosine theta plus cosine theta, sine theta.
Beautiful. Thank you. All right, so we have this, but one thing we might notice, I have a sine cosine, and separately, I have a cosine sine. These two are the same thing. So really, I have two of the sine theta, cosine theta. And another way that I can write sine theta plus theta is sine of 2 theta. All right. So where does this sine double angle formula come from? It is a special case of the sum difference formula for sine. Okay. In other words, if you know your sum difference formula, you know your double angle formula.
That's the sine sum formula, right?
Yeah, the sine sum formula. All right, let's take a look at the tangent one before we get onto the cosine one, just because there's only one version of the tangent one. All right, so can I get someone to tell me from the lecture on Monday, tangent of alpha plus beta, what is that formula? And let's go with the version that has the tangents in it. Okay, let's go with the versions that have the tangents in it.
It's tangent alpha plus tangent beta over 1 minus tangent alpha times tangent beta.
Beautiful. All right, we've got our alpha ones here. We've got our beta ones here. All right, and so let's play the same game. Let's say, what if we had tangent of theta plus theta instead? What would that give us if we plug that into the formula?
It would be tangent theta plus tangent theta over 1 minus tangent theta times tangent theta.
Beautiful. All right, and if we peek real quick at what we had for the double angle formula for tangent, how do we get this 2 tangent on the top? Well, we have 1 tangent plus 1 tangent, right? That makes 2 tangents. And then how do I get this tangent squared theta? Well, I take tangent and I multiply it by tangent, all right? So in other words, we can say that tangent of 2 theta is 2 tangent theta over 1 minus tangent squared theta. All right. So with the sine and cosine, or the sine and tangent formulas, we can literally plug them into the sum formula. But instead of having 2 different angles, we have 2 of the same angle, and now we have a double angle formula. Okay. We can play the same game with cosine, but I also want to talk about how we get those other versions. Okay. So with cosine, we have cosine of alpha plus beta, and this one should be cosine alpha cosine beta minus sine alpha sine beta, right? And we have, these are where our betas go, and this is where the alphas go, right? And we play that same game and we say, what if we put in 2 of the same angle and they both happen to be cosine? We would get cosine theta minus sine theta, right? And we'll get cosine of 2 theta equals cosine squared theta minus sine squared theta. And this, my friends, is one of the versions of the cosine double angle formula. Okay, so if we peek back up here, we have cosine squared minus sine squared, which is the first one of these versions. Okay. Now, one of the most common identities that we've used, right? And I'll go ahead and write it here, is we had sine squared theta plus cosine squared theta equals what? What did we have that equal to?
That equals 1 minus cosine squared theta.
Just this, cosine squared plus
Oh.
cosine squared.
Just 1.
Yeah, just 1. Okay, so we have this equals 1, but we can, as you were already thinking about, write it in some different ways, right? So in particular, I could say sine squared theta equals what? Like, what's a way that I could write sine squared theta?
1 minus cosine. Well, cosine squared theta.
1 minus cosine squared theta, great. And from the same starting point, how could I write cosine squared theta? If I go back to this Pythagorean identity, what happens when I get cosine squared all by itself?
It's 1 minus sine squared theta.
Beautiful. Okay. Now, we've kind of used this in some of the identities we've already proven, right? But we're going to be able to use these to rewrite our cosine double one to make the other versions that we have, okay? So in particular, oops. All right, instead of cosine squared, okay, instead of cosine squared, I'm going to write 1 minus sine squared. And so I'll get 1 minus sine squared theta minus sine squared theta. And if I simplify that, I get 1 minus 2 sine squared theta. Okay. So if I were to annotate this, I would say I used the Pythagorean identity, and then I used some algebra, and I got to 1 minus 2 sine squared. Now I can start at the same cosine squared minus sine squared. And this time, instead of substituting the cosine squared, I'm going to substitute the sine squared. All right, so I could also do cosine squared theta minus, instead of sine squared, I'm going to put 1 minus cosine squared. All right. And if I do a little bit of algebra here, I'll end up with 2 cosine squared theta minus 1. Right, so we did Pythagorean, and then we did some algebra. Okay. So for those of you who are like, I just really want to know the formulas, here are the formulas, right? And for those of you who are like, oh, it's easier to memorize when I kind of know where it comes from, here's just a little look behind the scenes of where they come from, okay? All right, so let's move on to some practice problems. Oh, why is that not updating? There we go, okay. So finding exact values for double angles. All right, I want to be really clear here before we get too far into this, that this is going to be a non-calculator situation. Okay. So the expectation as we move through these is that we're able to do these without a calculator. All right. So let's take a look at this first example. If sine alpha equals 4/5 and alpha is an acute angle, find the exact values of sine 2 alpha, cosine 2 alpha, and tangent 2 alpha. In other words, we want to find the values for the double angles, right? Then determine the location of 2 alpha, all right? So let's go back and take a look at this and maybe write down some things that we know. So when I look at this, sine alpha equals 4/5. I also know that sine alpha equals O/H, like opposite over hypotenuse, right? Now, when someone says that alpha is an acute angle, what do we know about alpha? Like, what is the smallest alpha could be, and what's the biggest alpha could be?
It's between 0 and 90 degrees.
It is precisely between 0 and 90 degrees. Okay. All right, so now we want to find the exact values of those double angles. And so if we were to sort of describe some steps to do this, the first thing that I hope that we see is a diagram, okay? We have a diagram. If my angle is between 0 and 90 degrees, what quadrant is that angle in?
One.
Exactly. So alpha is in quadrant 1. Okay. So let me draw a diagram that shows a triangle in quadrant 1. Okay. So we've got quadrant 1, and we can draw in the rest of the triangle, and then we could label this angle as alpha. Okay. Now, based on what information you have for sine alpha, where can I put some numbers, and what can I put for those numbers?
For the diagonal angle, you can put 5, and then for the opposite or vertical one, you could put 4.
You mean diagonal side?
The hypotenuse.
Yeah. So we'll have 5 over here and then 4 over here. What do we know the length of the last side is? 3. Perfect, Matthew. Great, right? So this is a great example where I'm just getting started in this question. If I know the 3, 4, 5 triangle, I don't have to do any calculations, right? Now I can focus on the actual content that I'm working on here, right? All right, so we've got our diagram. We know that our angle is in quadrant 1. And now let's go ahead and figure out what sine of 2 alpha is. Okay, and so here's how we're going to do this. Sine of 2 alpha equals, someone give me the formula that we just wrote down for sine of 2 alpha.
It's 2 times sine alpha times cosine alpha.
Beautiful. All right, so we have 2 sine alpha, cosine alpha. Great. All right, so let's actually use our diagram to plug in some values. All right. What can I put in for sine alpha?
Can you use the 4?
You cannot use the 4, but you can use this diagram and think about what you know about right triangles. And yes, I argue you can put in 4/5, right? Sine of the angle is the opposite over the hypotenuse, right? It's only the y value when we have a unit circle, right? In other words, if this hypotenuse were 1, then we could just say that it's the vertical side, okay? So I have a 2 here. I'm going to sort of think ahead and make this 2 into a 2 over 1. And everywhere I see sine theta, I'm going to put 4 over 5. Right. What can I put in for cosine alpha using this diagram? Nice, 3 over 5, because we have the adjacent over the hypotenuse. Right. All right, we plugged in all our numbers. How do we multiply 3 fractions?
You do 2 times 4 times 3, and then that's the numerator.
And then we could do the same thing to find the denominator. All right, so we get 2 times 4 times 3, that's 8 times 3 is 24, over 1 times 5 is 25. And this, my friends, is your sine to alpha. Okay, so if you draw your diagram and you label all 3 sides, you will have all the information you need to plug it into the formula. And then you need to multiply your fraction. Okay. So let's try the same thing, but for cosine. All right, so cosine of 2 alpha. Now I know I said that there were 3 different formulas for the cosine one, right? So for this first time, I'm going to write out all 3. You're going to help me plug in the numbers. And then before we calculate anything, I want you to help me figure out which one of the 3 is going to be the easiest to calculate. That makes sense. Okay, so we're going to write all 3 out, but let's see which one becomes the easiest to calculate. So we have cosine squared alpha minus sine squared alpha. We also have 1 minus 2 sine squared alpha. We also have 2 cosine squared alpha minus 1. Right, those are my 3 options. All right, so I'm going to fill in all 3 options. If I do cosine squared, that would be 3/5 squared minus 4/5 squared. Right, so if I choose this one, it will look like that when I plug in the number. If I choose this one, it will look like 1 minus 2 times 4 over 5 squared. All right, and if I choose the last one here, I will get, I will get 2 times 3 over 5 squared minus 1. All right, that looks like a lot. And I just want to remind you, we're only going to choose one of them. All right, we want to choose the one that is going to be the most efficient for us. We don't want to do more work than we have to. Okay. Out of the pink one, the orange one, and the green one, which one do you think will be the easiest to do without a calculator? All right, we have 1 vote for the green. Do you mind sharing a little bit about why you think the green one is going to be the easiest or most efficient for you? Right, I see someone voting for pink. Great, same thing. Whatever you choose, give a little justification. Like, why do you think that one is going to be the most efficient, right? Because I think some of us are really good at making this decision, and other people are like, I would really like to know how people make this decision, right? So it is important that we talk about not just how to do it, but why we're doing things.
I would choose pink just because I feel like it would be easier to square it, as well as they both are like over 5.
Mm,
So yeah.
okay. So let's write these out a little bit more, right? Because I think I'm asking you to do some thinking in your head, and maybe you need to write out some scratch work here, but let's just try expanding these and see what we get. So if I expand the pink one, I'm going to get 9 over 25 minus 16 over 25. Right? If I expand the orange one, I'm going to get 1 minus 2 over 1 times 16 over 25. And if I expand the green one, I'm going to get 2 over 1 times 9 over 25 minus 1. Right. Now, I think that both Ellie and Dallas noticed something about that denominator. Right? When we're adding fractions and subtracting fractions, when you first learned how to do that, the quote unquote easy questions were the ones where your teacher gave you the same denominator, right? You didn't have to do any work. As long as they had the same denominator, you could just subtract the numerator. Of these 3 cases, the pink one already comes with the same denominator, all right? Now, this is where we have like a little bit of personal choice. For me, the fact that it has a single denominator already, like the same denominator, makes it so much smoother to do in my head. Can I do the one in the orange? Sure, I can multiply and then find a common denominator. Can I do the green one? Sure, I can multiply by 2 and then I can find a common denominator. Yeah, I can do those things, just like I know you can do those things. But look at how much ink we've already used on this question, right? If we want to choose the one that is the least amount of writing, maybe, I think that the one in the pink will give us the answer in the fewest number of steps, right? Now, that's my personal choice. It sounds like some of you also resonate with that choice. If you choose to do the one in the orange, no big deal, that's fine. If you choose to do the one in the green, no big deal, that's fine, right? But at the end of the day, we should all get the same answer, -7 over 25, okay? So when you're looking at the cosine one, you only have to pick one of them. You want to use the pink? Do you want to use the orange? Do you want to use the green? I'll leave that choice up to you, okay? But as we work through a lot of different cases, try and see which ones get you to your answer the most efficiently, all right? All right, so let's squeeze in tangent over here. Not that it's less important, but I think talking about decision-making for the cosine one is important. We'll label this one as 4 tangent of 2 alpha equals. Now I know there's a whole big formula, right? We talked about this formula. We have 2 tangent alpha over 1 minus tangent squared alpha, right? And if I were to plug in all of those values, I would get 2 times 4 over 3 over 1 minus 4 over 3 squared. How many people feel like cranking through that right now? I wouldn't want to. And I argue that there is a more efficient way to answer this question. And in fact, if we have sine and cosine, we already have our answer for tangent. What do we know about how sine and cosine relate to tangent?
Tangent theta equals sine theta over cosine theta.
Bingo, you got it. All right. So kind of like you can do the green one if you want. No one will be mad at you. You can do the orange one if you want. No one will be mad. But you might get more problems done more quickly if you use the pink one, right? Sort of the same idea here. You can use the tangent double angle identity. Nothing wrong with that. Really great practice in multiplying fractions, finding common denominators, etc., etc. But check this out. Tangent 2 alpha equals sine 2 alpha over cosine 2 alpha. Because tangent by the quotient identity is sine over cosine. And look at what we already have. We have sine, we have cosine. So all I'm going to do is do 24 over 25 divided by -7 over 25. I can write that as 24 over 25 times -25 over 7. I hope we cleverly reduce here before we start multiplying numbers out. All right, this is something I noticed on that exam. Some of us multiplied things out the long way, and it took more time. It's not wrong, but it took more time. All right. What can I reduce before I start multiplying things?
You can eliminate the 25.
You got it. And therefore, we end up with -24 over 7 for our tangent. Okay. If you want to do it using the identity, you should get the same answer. But if you've already put the time and effort into finding sine and cosine, why not use your work to find the tangent one? Okay. I know this looks like a lot of writing, but remember, for cosine, you just need to pick one of them. And for tangent, you just need to pick one of them. You don't need to show all three. You don't need to show all two, just one of them. Okay. All right, last question here. Determine the location of 2 alpha. That is, I want to know what quadrant 2 alpha is in. Okay. Well, how do I know that? I have a positive sine value, a negative cosine, and a negative tangent. What quadrant has sine being positive, cosine being negative, and tangent being negative?
2.
Yeah, quadrant 2. All right, so what we know then is that 2 alpha is in quadrant 2. Okay. I think what makes this question either not so bad or really challenging depends on how you did on that first unit. For those of you who really put in that time to know like all these different relationships, like the quadrants and the signs, knowing your special right triangles, and knowing how to multiply fractions, knowing SOHCAHTOA, we used all of that to answer this question. The only new part was really just a new formula that we were plugging things into. Okay. This kind of thinking where we layer on one small thing and then we use all the things that we ever learned before is very similar to the flavor of calculus. Okay. And that's why I'm so glad that we get to do 104 right before we walk into Math 150 in the spring. All right. This kind of thinking, like what tools do I know? How do I use them? Are all going to be really beneficial for us in the spring. Okay. So that being said, let's try one more question. All right, and then we will take our first break. So let's take a look at this one. If tangent of theta equals -3/4 and theta is in quadrant 2, find the exact values of sine 2 theta, cosine 2 theta, and tangent 2 theta, then determine the location of 2 theta. Okay, so very, very similar to the previous question. In fact, we can pretty much use all of the same steps, except in between, our picture might look different. We might have different numbers, but that's it. Like the structure of what we set forth for ourselves will remain the same. All right. So we're going to start with a diagram. Then we're going to find our sine 2 alpha, our cosine 2 alpha, and our tangent 2 alpha. All right. So let's begin with our diagram. And we know in this case, we want to draw in quadrant 2. Oops. All right, so let's get that XY grid in there. Right, and I'm going to be really careful to draw my triangle so that it is somewhere in quadrant 2. All right, and make sure that I create my right triangle, and I'm using alpha this time, all right, or theta rather. Theta or whatever angle should always be touching the origin. Okay. Now I have a few numbers to write here. Tell me what I write where. Where do I put those numbers?
Three goes on the vertical line and 4 goes on the horizontal line.
Great. I agree with you like 90%. Right. So right now we have a suggestion. This should be 3 and this should be 4. We need one small symbol to make this accurate.
4 is negative.
You got it. 4 is negative. Okay. Now, how do I know the 4 is negative? Because I'm going in the negative X direction. All right. And that's why I've been really picky about how you draw your triangle, because sometimes all the numbers are positive and it doesn't matter. But sometimes some of those numbers are negative and we need to know which ones. Okay. Great. We've got a 3, a -4. I argue that we know the length of that third side.
5.
You got it. Right? We know it's a 3, 4, 5 triangle. We can label that. We don't even have to use Pythagorean theorem. Okay. So let's go back now. Let's go ahead and take a look at our sine 2 theta. Let's write out that formula. It is 2 sine theta cosine theta. All right. I'm going to make that 2 into a 2/1 because I'm cleverly thinking ahead that I'm going to need to multiply some fractions. What do I put in for sine theta? What do I put in for cosine theta?
Sine would be 3/5. 5.
3/5, I would agree. All right. And our cosine? -4/5. Nice. All right. Now we multiply all the way across, and I believe we get -24/25. Okay. Great. Let's do our cosine double angle. All right. Again, you can choose pink orange or green. I will leave that up to you. I have a personal preference for the pink for my own computation, but you can use the orange one. I will not judge. You can use the green one. I will not judge. Okay. So if I do the cosine one, I get cosine squared theta minus sine squared theta. All right. I know my cosine is -4/5. I'm going to square that. Minus sine is 3/5. And I'm going to square that. And that gives me, what do I get for the first term here?
You get a 16/25.
Beautiful. I love that you also didn't say that it was negative, right? That's something that sometimes we forget, especially if we rely on a calculator. If we type it in wrong, all of a sudden we get a negative here, right? But when we square a negative, we get a positive. So we get 16/25 minus 9/25, which gives us 7/25. Okay. Now we've got our tangent, double angle. Again, whoops, we have a formula for that. I would have no problems if you use that formula, none at all. I'm more just, I want to get to the answer as quickly as possible. And since I already found my sine and cosine, I'm just going to divide them. Okay. Again, that's a personal choice. But if you find that sometimes you don't have enough time to finish a question, sometimes it is worth saying, okay, is there a faster way, right? And so I could say sine 2 theta over cosine 2 theta, which is -24/25 over 7/25, which I can write as -24/25 times 25/7. Well, Judy said this is no calculator, so I better look to see if I can reduce first, because it might take me a while to multiply out 24/25. Good thing the 25s reduce, and we get -24/7. Okay. All right. The last question we want to ask ourselves, what quadrant has a positive sign? Oh, sorry, not a positive sign, a negative sign, a positive cosine, and a negative tangent. Great, that is quadrant 4. And so now we've answered all parts of the question. We found the exact values, and then we determined where 2 theta is going to be. All right. I don't know how big 2 theta is. I just know it's going to be in quadrant 4. Okay. All right. So before we go on break, I have a question for you all. We have one more example like this. All right. It is very similar in flavor. Is that something that would be helpful to go over again when we come back from break, or would we like to move on to something different? All right, I have one move on. If you feel differently, you can message me directly. All right, but we will take a break right now and sort of decide when we come back. Right now it is 10:33 almost. So let's be back at 10:45. All right, we'll be back at 10:45. We'll do some verifying identities, which I know is everyone's favorite. Oh wait, that's just me, my favorite. And then we will talk about half angle identities. Okay, so I'll see you folks back here at 10:45. All right, so example 3 here, we'll just say is extra practice. Check with Judy for answers or, whoa, or questions. All right. I know that not everyone takes me up on that, and that is absolutely fine. I do always appreciate when people come back and they're like, oh, I actually did do this question, and I actually realized I did have a question about how to do that, or is this answer correct? And so that's something that, you know, you can use to study for the next exam, or also just do for extra practice just for you, or not if you feel like between the quiz and this, you got it, okay? All right, so moving on, let's take a look at verifying identities, all right? And so again, the way that I'm modeling the writing is something that I hope we really start to do consistently, all right? When we are writing these verifications, it is important that we know like why we're making the choices we're making, all right? Like what identities help us do that. And sometimes it's just algebra, and it's okay to write algebra, but we always want to pick only one side. So either we're going to work with the left side or we're going to work on the right side. But one thing I noticed is some of us are sort of moving terms back and forth between the sides, and unfortunately, that is not allowed. All right, we really want to make sure we're picking one side and working with that one side. And so as we begin, I would say for example 4, you can work with either side. I think I chose to work with the left-hand side, but that's mostly because if I think about this other side, sometimes I worry like, what if I have to add a fraction, then I need a common denominator, and that's just not something I really want to deal with. So I tend to pick sides that I work with like multiplication of things, okay? And so looking at this, if we unpack this left-hand side, we have cotangent of x. What is another way that I can write cotangent? I could write it as 1 over tangent for sure, okay? Now let's look at the right-hand side though. Do I see anything with a tangent on that side? And I would say, I don't think so. I don't see anything with a tangent, all right? So it's not wrong to say, and I'll write this up here, cotangent x equals 1 over tangent x. There's nothing wrong with that. But someone tell me another way that I could write cotangent.
Cosine x over sine x.
Okay, that's a different way. I believe that cosine x over sine x. Okay. So let's pause here for a moment, okay? Because I feel like we did really well with the decision making in the previous section, right? And what I mean by that is this, when we were choosing either the pink way, the orange way, or the green way, we knew we could do all of them, but some of them got us to the answer a little bit faster, right? And so if we think about identities, we actually make a lot of these same decisions along the way. Meaning, if I look at the right-hand side that I want to match, I don't see anything with tangent. So you could write 1 over tangent, but maybe it would be more helpful if you wrote the one with cosine and sine, right? And part of that is like the more the questions that you work on like this, the easier it is to make that decision, okay? Now, I know I say this a lot, and I think some of us have either been able to put in the time or maybe grasp it just a little bit more quickly. And I think some of us are still kind of struggling with that decision-making piece. If you feel like you're struggling with the decision-making piece, I would really encourage you to come hang out with me during office hours, and we can talk this through and write out all the messy versions and just kind of do some problems together. Like I would be more than happy to do that. All right. truth be told, I went to office hours for a class that I'm taking yesterday, and I walked in and the professor was like, "What questions do you have?" And I was like, "I don't know. I know none of this. Like, I don't know how to do any of this. Can we just start from the beginning?" And it was kind of embarrassing. I got a little sweaty. Like, I didn't like being that person, but I walked out of office hours with 1.5 questions done instead of 0 done. So it was embarrassing. I kind of had to put my ego aside and put aside the fact that like I'm worried my professor is going to think I'm an idiot, but also he helped me work through the stuff that I needed to work on, right? And so at the end of the day, I got what I needed, which is how to be better at the kind of math that I'm working at, okay? And so in this case, let's kind of return to this question, our cotangent. Let's do a little color coding here so we can keep track of what becomes what. This cotangent, let's say we write it as cosine over sine, okay? Making that substitution. Now, what about sine 2x? What can I write instead of sine 2x? And this we just learned today, all right? So this is a new formula for us. Great. 2 sine x cosine x. All right. Now, I'm going to model for you what I hope you do as well. Write down the other side. Okay, write down that other side. If you choose not to write it down, know that you are choosing to lose points. I want to be clear about that, all right? So you can be mad about having to write it, but will you be more mad to write it or more mad that you lost points? I'll leave that up to you, okay? So the annotation here, we could say that we have a quotient identity here, all right? And we could say here that we have the double angle. Right. All right. What can we do to that left-hand side? Great. I do see a sine x in the numerator, and I see a sine x in the denominator. And then that allows me to rewrite the left-hand side. What do I get when I rewrite the left-hand side? Great. 2 cosine squared x equals 1 plus cosine 2x. All right. Now we have to continue working on the left-hand side. All right. So over here, I know eventually I want to get to a cosine double angle. Okay. And I know that I have some choices to make the double angle identity happen. All right. How many of those choices to make the cosine double angle have a cosine squared in it? Let me ask that question one more time. How many of the 3 choices we have for the cosine double angle have a cosine squared in it? 2 of them, okay? Of those 2, let's write those down, all right? So cosine 2x is cosine squared x minus sine squared x. That's one of them. I have 1 minus 2 sine squared x, right? And I have 2 cosine squared x minus 1. So of those 3 versions, I probably don't want to pick the one with the sine squared, right? Are there any signs on the right-hand side? I don't see any signs where we're going, so maybe I don't use this one either. Okay, well, I have one left to choose from. 2 cosine squared minus 1. That looks pretty similar to the left-hand side that I have here. How do I make these two look the same? I cannot move things. I cannot touch that right-hand side. But you've got the right idea though. Why did you want to move the 1 to the left-hand side? Right? Why did we want to move that 1 to the left-hand side? Yeah, we want to make it match, right? We had a -1 here, and this one doesn't have a -1. So here is a way that we can make them match, okay? 2 cosine squared minus cosine squared x, all right? I want to make it match up here, so I'm going to do -1. But I did something that changed that left-hand side. So now I'm going to do something that will make it the same again. All right, so let's pause for a moment. -1 plus 1. What does that give you? 0, okay? Fancy 0. I added 0. I didn't change anything, but I did make it so that I could match what I wanted to match. Okay. Now, this 2 cosine squared minus 1, I can write as cosine 2x. Now, when I switch the order, it still stays the same. So I get 1 plus cosine 2x equals 1 plus cosine 2x. Victory box. We are done. Okay. So one thing that we can see is, yeah, we have to know the identities. But as we go along, we're going to find some more quote unquote clever tricks that we tend to use a lot. All right. One thing I've seen a lot of us master already is like the reducing. We're pretty good at that. Seeing people be really good at the conjugate. All right. And now one tool I want us to add to this is this idea of a fancy 0. All right. All right, let's take a look at the second example, example 5, okay? So example 5, I have a left-hand side, I have a right-hand side. Now, based off of what we just talked about, right? How I like to work with things that are multiplication. I'm going to choose to do the right-hand side this time, okay? You can make a different choice. It would take you some different steps to get to the same answer, and all those ways are okay, all right? But here's why I like to work with the multiplication side. So I'm going to be diligent. I'm going to go ahead and write down my left-hand side. But on the right-hand side, I end up with sine theta plus cosine theta times sine theta plus cosine theta. And now this is like a FOIL situation, right? I just need to FOIL things. So I FOIL them out. Help me out. What do I get when I FOIL out the right-hand side?
Sine squared theta.
I agree. Keep going.
Plus sine theta times cosine theta
Mhm,
plus cosine theta times sine theta
mhm.
plus cosine squared theta.
Great. I agree with that. And I say there's one more way we can simplify that even a little bit more. There we go. We could combine those two middle terms. All right. All right. So let's keep in mind what we're trying to match. Okay. What do people see here? Other than a ton of letters. Nice, nice observation. I love that, right? One of our bread and butter identities that we use all the time, sine squared plus cosine squared gives us 1, right? So in fact, this sine squared plus this cosine squared will actually make the 1. Okay. All right, and then I see, there we go. How many times have we seen this one today, right? Our sine double angle. They're already a match. All right, so we've got, let's go back and write this out. We have our Pythagorean identity, and this one is our sine double angle. All right, and now we've got the left-hand side equals the right-hand side. Victory box, we are done. Okay. All right, let's try one more of these. Let's take a look at example 6. Okay. All right, so for this question, I think we can go about it in a few different ways. All right. I'm going to choose to start on the left-hand side. And the reason why I'm choosing that, I hope will become a little bit more clear as we move on. I could write cosine 4 theta as cosine of 2 theta. Do we buy that? That cosine 4 theta is the same as cosine 2 theta. Why would I want to write it as 2 times 2 theta?
So that we can substitute it with something else.
Yeah, in particular, a double angle identity. Great. Why did I choose this version of the cosine double identity? Like, how come I didn't use cosine squared minus sine squared? Or how come I didn't use 1 minus 2 sine squared? Like, why did I choose this one? Exactly. There's no signs on the other side, right? So could I have written over here 1 minus 2 sine squared? Yeah, that's mathematically correct, but is it getting me closer to the other side? I don't think so. Okay. And so it's exactly that kind of decision making I want to make sure we practice here. Okay. All right. So let's continue. All right. I'm going to do a little rewrite on the left-hand side, and I'm going to get 2 cosine 2 theta squared minus 1 equals what I have on the right-hand side. Okay. Why would I write it that way? I bet I can make another substitution. Cosine 2 theta. Right? In fact, we used our cosine double angle twice. I'll give you a moment to FOIL this out. All right, keep in mind there's still a 2 in the front and then a minus 1 at the end. And once you have that FOILed, what do we get on that left-hand side? All right, what do we get?
Are we foiling just the cosine squared theta? Oh, I just noticed that I didn't write the other squared symbol. I got 4 cosine to the power of 4 theta minus 4 cosine squared theta plus 1.
All right. I agree with that. That is what I got as well. So let's just kind of keep track of where that term went. All right. Last step. Let's do some algebra. And by that, what do I mean when I say do some algebra? Like what are we going to do in this step? Great, we're going to distribute, and we're not going to forget about that minus 1. So we get 8 cosine to the 4th theta minus 8 cosine squared theta plus 2 minus 1. And then that's that one last step. 2 minus 1 is literally the last step to make these two sides equal. We get 8 cosine 4th theta minus 8 cosine squared theta plus 1 equals the same thing we wanted on the other side. Victory box. We have verified this identity. Right. So I want to pause here for a moment and just see if there are any questions on the verifications here. All right, I think that, again, some of us were sort of like finding this to be very confusing. Like, how do we make all these decisions? If that is how you are feeling, I would really encourage you to stop by office hours or go to tutoring if that feels less scary. But there will be a lot of points on this second test on verifying the identities. Right, so I just want to make that expectation really clear. A lot of things on this second exam will be around verifying the identities, both with someone else, but also independently. And that's the part I really want to make sure that we're able to reason through these problems. Okay. All right. There are no other questions. Let's go ahead and take a 10-minute break. And then when we come back, we'll finish up with the half angle formula. Okay. I know this stuff is so dense. I also know that you're like sitting in class for 3 hours, and that's just a really, really long time. All right. So let's come back at 11:28 a.m. All right. And then when we come back, again, I'll sort of scroll ahead so we can see we're going to be looking at the half angle formulas. and applying that. All right, we won't really use them in a lot of verifications, but we'll just practice doing some examples, and it'll feel similar to sort of how we started the class today. Okay, so we'll meet back here in about 10 minutes and take a look at this last chunk of class. All right, so we have our half angle formulas. All right, so I ask you the same question I asked you earlier, which is, what about this formula might tell you that you're looking for half angles?
It's like divided over 2, the angle.
Exactly, right? We have a half of theta, we have a half of theta, we have a half of theta. And sometimes these things seem so obvious. You're like, why is she asking these dumb questions? But at the same time, sometimes we just like don't look at these details. We're so busy trying to memorize these formulas that we actually forget what clues to look for, okay? That's why I'm pointing these out. Now, one of the things I do want us to notice here is that every single one of these formulas has a plus or minus in front, right? Now, I think the most common way that we've seen that is in the quadratic formula, and we use both the plus and minus, right? But I want to make one thing really, really clear here. Your answer will be either plus or minus, but not both. Okay, so this is different from the quadratic formula in the sense that we only have one answer. It's either going to be plus or it's going to be minus. Okay. To choose plus or minus, determine the location of theta over 2. Okay. So we're almost reversing our decisions from our double angle, that we're going to use whether, like, what quadrant is that half angle in? That will tell us whether it should be plus or minus. Okay. Now you'll notice here that the next chunk said, where do these formulas come from? And I'm just going to tell you, these come from the reduction formulas. All right, these come from the reduction formulas, which again, you will use in Calc 2. All right, so I'll tell you what the reduction formulas there are, but we won't really see them again until you get to Calc 2. Okay. All right, so let's figure out how we find exact values for these half angles. This is going to be really similar to what you did on Monday with the sum and difference formulas, but now we're looking at precisely half of things. We don't have to think about what we're going to add and subtract together. We're just cutting something in half. Okay. So let's start with example 7. We've got sine of 15, and knowing that these are in the half angle category, I could write this as what angle divided by 2? Precisely. So 30 degrees divided by 2. That means that 30 is our theta, right? So theta is the one that you use in all of these formulas. All right, so we have this. We're going to put a plus or minus in front because we're going to choose at the end. And sorry, I zoomed in maybe too much, too fast. Let's write down that formula for the sine half angle. Plus minus the square root of 1 minus cosine theta over 2. All right, let's go ahead and replace that value. So cosine of 30 degrees over 2. All right, Bust out that unit circle. Someone tell me, what is cosine of 30 degrees? Good, √3/2. Okay. So that we don't have to continue writing plus minus, let's actually figure out at this point whether it's going to be positive or negative. So sine of 15 degrees. What quadrant is 15 degrees in? Good. 15 degrees is in quadrant 1. So that implies, do we have a positive sign value or a negative sign value? Good, we have a positive sign value, okay? So this part in the pink is our decision of which one this is. Is it positive or negative? And so we can see from here that it's going to be positive. So I'm actually going to go back in. I'm going to put that positive sign right there. So we know we've made our decision, okay? Now at this point, we got to do some algebra. We got to work with our fractions. We got to work with our square roots and simplify this, okay? So we bring it back over here. Maybe the first thing, excuse me, that I would want to do is in the numerator, I would want to make a common denominator. And so I would get 2 minus √3/2 all over 2. Okay. And so in particular, this numerator became this numerator once I have a common denominator. All right, well, I'm going to do 2√3/2 times the reciprocal of the bottom. Did I do that right? No. Okay, so in the bottom I have 2, so this reciprocal should really be 1/2. Okay. All right, we look to see, is there anything that we can reduce? I don't think that there's anything we can reduce. And so we proceed and we get 2 minus √3/4. And I can take a square root of 2. So I'm going to do this. Square root of 2 minus square root of 3/2. Okay. So a good chance to practice our trig values, all those things from the unit circle, but also feeling confident enough that you have all the skills it takes to work with some fractions, some square roots, and even, look at this in our answer, we have a square root inside of another square root, right? But we are capable of doing that. We just need to trust in ourselves that we are grown up enough to write that down and it's going to be okay, all right? So that's a pretty fundamental question, very similar again to those like sum and difference angles that you practiced on Monday, okay? But let's try one that's a little bit of a different flavor, more similar to what we saw at the beginning of class today, all right? And so if we look at this question setup, for example, 8, we've got if tangent theta equals 8/15, and theta is in quadrant 3, find the exact values of sines of half angle, cosine of the half angle, and tangent of the half angle. And it's in fact so similar, we're going to start with the same thing. We're going to start with a diagram. Okay. And in fact, we are going to say, our theta is in quadrant 3. So we want to make sure that our diagram matches that. So I want to make sure that my angle comes from the origin, that I draw the right triangle part of it. I label this as my theta, all right? Where do I put the numbers that I have so far, the 8 and the 15? Great. All right, 8 is opposite, 15 is adjacent. But again, I'm going to say that is almost correct. What do we need to include here to make sure that the numbers we put match our diagram? Precisely, these are both negative, right? And the reason why we know is this is a negative x direction, right? And we know this is a negative y direction, right? And so in the beginning, when I was like, you gotta draw the triangle this way, I'm sure it was like, oh, why do we have to draw it this way? But maybe now that we see we're using it, right, in a different way, it is important for us to know whether things are positive or negative. And if we just draw it in the positive negative direction, we've done that work for ourselves already. Now, this is one of those triangles that is quote unquote a nice triangle, less common than the 3, 4, 5 one, but also one that pops up quite a bit. In fact, I think this was on your last exam. Does anybody happen to know what the length of the third side is? If you don't know, you could look up Pythagorean triples.
17.
What's that?
17.
It is 17, you got it. All right, so 8, 15, 17. I would say this is like among the least nice of the nice triangles, but it is one that comes up quite a bit. I think we can only work with 3, 4, 5 so much before we're like, oh, everything is 3, 4, 5, right? So I want to just like throw a little variety in there with the 8, 15, 17. But once we've got our diagram, what I want us to do is start to think about where my half angle will be. Okay, and so here's how we're going to set this up. I know that theta is in quadrant 3, right? But another way of saying that is that theta is between 180 degrees and what? What's the upper bound of theta? It can only be in this quadrant. Yeah, can't be any bigger than 270. Okay, so now let's figure out where theta over 2. Okay, and here's how I want you to do this. Theta over 2, all right? I took theta and I divided it by 2. Guess what I'm going to do to the 180? I'm going to divide it by 2. So what's my lower bound for theta over 2? 90. Good, because I cut that in half. All right. What am I going to do to the 270? Same, right? And by same, we mean we're going to divide it by 2. Well, what's 270 divided by 2? Okay. So we divided everything by 2. We see that our angle has to be between 90 and 135 degrees. What quadrant is that in? Good. We are in quadrant 2. All right, so all we did is we took what we knew about our regular angle, we cut everything in half, and then we said, where is that new angle? Okay, so we just cut everything in half, and we got the location of our new angle. I want you to tell me a little bit more. Okay, let's do a little bit more pre-thinking here. Sine of theta over 2, cosine of theta over 2, and tangent of theta over 2. If my angle is in quadrant 2, is sine positive or negative? Great, it is positive. All right, so I know I have the plus minus in front of my square root, but I'm saying I know that it's plus. All right, tell me about cosine. Is cosine in quadrant 2 positive or negative? Great, we've made our decision. We don't need to write plus minus in front. We know it's going to be minus. All right, what about tangent? Tangent in quadrant 2. Also minus. Great. All right, you have set yourself up for so many decisions that we're going to make in finding our half angle value. Right? You've made so many of those decisions right up front. And I want to see this kind of thinking. I want to know that you know how to reason through that problem. Okay. So once we find all of that pre-thinking, now let's go ahead and find sine of our half angle. All right. And all we're going to do, we're going to grab the half angle formula, but in front of it, we're going to put a plus sign because we already made that decision. All right, so I'm going to get equals a positive square root 1 minus cosine of theta over 2. Where do I get my cosine theta value from? I get it from my diagram. According to my diagram, what is cosine of theta?
Negative 15 over 17.
Perfect. All right. I love that you caught yourself there with that negative, right? Because we're all going to do that at some point. We want to make sure that we get that sign correct. All right. Let me just squeeze this over a little bit. All right. And now we do some algebra. 17 over 17 plus 15 over 17 all over 2 equals. All right, I'm going to do 2 things at the same time. I'm going to add my fractions here. So I'm going to get 32 over 17. And at the same time, I'm going to say instead of divided by 2, I'm going to do times 1/2. Okay. Over the next few weeks, I am going to start to skip a few steps here and there, right? Like in the beginning of the semester, I probably would have written out every single step here. But now I'm talking through more of them and doing less of that writing. But that means you can go back to the notes and like add in your own steps. Okay. All right. Let's use the same clever trick that we've been using, which is before we just start multiplying everything out, can we reduce? Right? Can we reduce?
I think 32 and 2 reduce.
They do. And what do they reduce to?
16.
Beautiful. All right, so we get the square root of 16 over 17, which we can say is 4 over a square root of 17. Okay. So that's how we work through the sine half angle. Very similar to the double angle one, except there's just a little bit more decision making up front. Okay. All right, let's find cosine of theta over 2. We know from our decision making up front, it's going to be negative. And we get negative square root of 1 plus cosine of theta over 2. We get negative times the square root of 1 minus 15 over 17, which gives us negative 17 over 17 minus 15 over 17 over 2. We crank through some arithmetic, we get negative square root of 2 over 17 times 1/2. Oh, there's that same clever trick again. 2 and 2 reduce. I don't have to worry about multiplying out, right? We get negative, whoops, negative square root of 1 over 17, which we can write as negative 1 over the square root of 17. And last but not least, tangent theta over 2. You are welcome to use the formulas that we have, right? You can use these formulas. Nothing wrong with that. Or you can say, I already did a bunch of work. I'd like to use that work, right? I know what sine of the half angle is. I know what cosine of the half angle is. So let me just divide those. And we'll get 4 over root 17 times negative root 17 over 1. All right, so this is me skipping some steps. I divide those two, but I know that means I'm going to multiply by the reciprocal. Reduce, reduce. We actually end up with negative 4 for the tangent of the half angle. Okay. All right, so let me leave this up on the screen for you for a little bit. And we have one more example like this. How are people feeling? Would we like to see the second example? Would that be helpful? Or are we like, we get the process, Judy, let's move along. Where are we at? All right, again, I've got one vote for a move on.
Could we work on it and then message you if it's correct?
Yes, absolutely, always, right? So we'll put this as practice. Feel free to reach out for help or solution. Okay. One of the things I do want to highlight here is I've seen some people put on their reference sheets just a bunch of formulas, which is fine. All right. Some people are really good at looking at the formula and knowing exactly when to use it. But one thing I noticed is that sometimes we don't always know like what order to do the steps in or something like that. Like, you know, we maybe make a mistake on a quiz and then we make the same mistake on an exam. One way around that might be to just list out these steps right? Number 1, draw a diagram. Number 2, find sine. Number 3, find cosine. Number 4, find tangent. Like all of those might be a different way for you to like on your reference sheet be like, okay, I know what I need to do when I see this kind of problem, okay? All right, so last bit then is the reduction formula, all right? And so I'm going to talk through this quickly. This will not be on the exam, the reduction formulas, but I just want to show you what they are so you know what they are. And then if anybody wants to stay around, I will do an example of a question from Calc 2 where you would use these reduction formulas. Okay, you don't have to stick around for that part. That is entirely voluntary. I know we're all in different like sort of moments in our life, but also where we're headed with mathematics. Okay, so here's the rundown on the reduction formula. So we see this in Calc 2, all right, and they come from our double angle identity. All right, so let's start with the cosine one. The one that is 1 minus 2 sine squared theta. Okay. What we're going to do is we're going to solve for sine squared theta. Okay. So I'm going to take this and I'm going to add it to the other side. So I get 2 sine squared theta equals, I'm going to move the cosine to the other side. 1 minus cosine 2 theta. Since I want to get the sine squared by itself, I'm going to divide by 2. This, my friends, is the power reducing identity for sine. Okay. Now the size of the numbers that you write is actually very important here. This 2 is sine squared, right? It is to the power of 2. This 2 in front of the cosine is a double angle. It is not a power. So the reduction means you go from a power of 2 to a power of 1. That's where the name comes from. Okay. So let me say that one more time. The power reduction, the reduction part is you went from a power of 2 to a power of 1. All right. We're going to use the other cosine double angle one to do the cosine reduction formula. We're going to do the same game. We're going to get cosine squared by itself. So we have 2 cosine squared theta equals cosine 2 theta plus 1. And to get cosine squared theta by itself, I'm going to divide by 2. That, my friends, is the power reduction formula for cosine, right? This 2 is not a power. The green 2 is not a power, but this yellow 2 is a power of 2. All right, last but not least, we're going to use the same strategy we've been using to get the tangents, which is take what you know about sine, divide it by what you know about cosine, and we'll end up with 1 minus cosine 2 theta over 1 plus cosine 2 theta. All right. So these formulas, all right, in particular, the ones for sine and cosine, these two come up most frequently in Calc 2, all right? Sometimes you see the tangent one, but again, if you know sine and you know cosine, you just divide it to find tangent, and that's it. Okay. All right, so again, this last part, the reduction part, will not be on the exam. But for those of you who want to make it to and through Calc 2, just be aware that this is going to come up again. Okay, it just has a better application in Calc 2, and it's not necessarily something that we need to study a bunch right now. All right. So that being said, I will stick around for a little bit in case anybody wants to see the Calc 2 example. If you don't want to see that, have a great rest of your day. I will see you later.
Thank you. Have a good day.
Of course, see you later.
Thank you.
Bye.
Can you hear me?
Yes.
Okay. I was wanting to ask about like memorizing some of this stuff. In terms of like, I remember you earlier talking about how you derive the double angle from the sum and difference angles. And then the double angle with the tangent, you can pretty much just use the other double angles that you had. And then for the half angles, you use the reduction, but for the most part, I guess visually it's kind of easy to memorize. And then for the tangent, you could just use the other two.
Exactly.
So is that kind of like a good recommendation, is like really get down the first two, or the sine and cosine for sum and difference, double angle, and then half angle?
Yeah.
Okay.
Really
Thank
good way
you.
of looking at that.
Have a good day.
All right, you too.
Hi, Professor. I had a quick question
Yeah, for sure.
about, it's mostly just about when we answer the questions on the quizzes. So